Hello and welcome to the week 1 review for Math 2414. This week is mostly going to be a review of content from your previous courses, along with maybe some slight introductory material, so it shouldn't be too hard or too lengthy. We'll start with just a really quick review of the plane. So the plane is composed of two axes. We have the x-axis and the y-axis, and both these axes are comprised of one copy of all the real numbers. So you'll often see the plane written as r cross r, or equivalently r2. Now, in the plane, we have 4 sections called quadrants: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And importantly, quadrant 1 is the place where both coordinates are positive. Now, let's talk quickly about coordinates. We have 2 coordinates for any given the xy plane. We have an x coordinate and a y coordinate. And this is important because it corresponds exactly to the dimension we have. We have 2 dimensions in R2 and 2 coordinates. Now let's kind of expand this to a new space. This space is 3 dimensions rather than 2. And correspondingly, we're going to call it R3. So whereas the plane has simply an x-axis and a y-axis, space has 3 axes. We have the same x-axis and y-axis, but now we also have a z-axis. So we're going to have a y-coordinate, a z-coordinate, and an x-coordinate. So our coordinates take the form x, y, z. And again, you'll notice we have 3 separate coordinates corresponding to the 3 dimensions of our space. In R3, we actually have, rather than the quadrants, we have what are called octants, because there are 8 octants. You can think of it as being, if we have the origin, we're going to have cubes. It's really hard to draw for me, but you can imagine we're going to have almost what's like 4 boxes stacked on top of each other twice. So we would have something like this, and then at the bottom of this contraption, we would have the origin there, and then another copy of this beneath it, kind of like that. Anyway, big takeaway is that there are 8 octants, and the only one you really need to know is that the first octant has x, y, and z all positive. So this is called R3. Now, often, when we graph something in the plane, it comes out as a line. But often, when we graph things in 3D, they come out as surfaces. So let's go ahead and do a quick little example of this. And again, we'll use kind of just a really basic example. If we compare the line y equals to x squared in R2, well, that's going to look something like this. Basically just a line. But if we look at z equals to x squared plus y squared, which is pretty similar, we still have this basic square. Rather than having a line, what we actually get is an interesting bowl shape, kind of like this. So you can almost think of it as being a parabola spun in a circle. Let's do another quick example. In this case, we're going to look at the equation in R2 x squared plus y squared equals to 1. If you'll remember, this is the equation of, and we're going to say that's a circle of radius 1 centered about the origin. It's not perfectly circular, but you get the idea. Now let's take a look at the analog in R3. And one quick note is in R2, this is still a line. But if we look at now the equation x squared plus y squared plus z squared equals to 1, this one's in R3. Well, now all of a sudden we have and then we would have our coordinate axes like this. This comes out as a sphere. Now, we're actually going to do one more example. What if we took this same equation, x squared plus y squared equals to 1, in R squared, and instead we graphed it in R cubed? Well, here we have our axes, and we know that if we just completely ignore the z value, we should just have a circle. So on our xy plane, I'm just going to sketch the same circle that we always have. But now I know that this equation is going to hold true for any z value as long as the x value and the y value stay unchanged. So what I can do is I can actually stretch this circle and as low as I want. And the shape that comes out is a cylinder, stretching up infinitely and down infinitely. So you'll notice a lot of things that were lines in R2 often become surfaces in R3. So again, remember 3D coordinates have 3 components, an x component, y component, and a z component. So this raises the question, well, in R2, if we have 2 points, let's say 1, 2, and 3, 4, we can tell the distance between them using the Pythagorean theorem. We take the square root of the difference between each component squared. And this would get us, in our example, 2 times the square root. Well, for 3 coordinates, the process doesn't really change at all. It's just that we now have a third component as well. So instead of 1, 2, let's say we had 1, 2, 3, and then -1, 4, 2. Well, then the distance between them would still just be the square root of the difference between the components squared. So -1 minus 1 squared plus 4 minus 2 squared plus 2 minus 3 squared. And all I'm doing is for this -1 minus 1, I took my point here and subtracted this here. That would get me 2 squared is 4, 2 squared is 4, and 1 squared is 1, which is the square root of 9, which is, of course, 3. For a more formal formula, if we have 2 points x1, y1, z1, and x2, y2, and z2, should be y1, and there we go, then we can say that the distance between them is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. All right. This is a more formal distance formula if you want it, but really it's just the Pythagorean theorem in 3 dimensions rather than 2. All right, let's go ahead and do a few practice problems. Go ahead and find the distance. And I'll give you a couple of minutes to work through those. All right, let's go over these. The first one is straightforward. We just apply our standard distance formula. 4 minus 1 is 3, 3 squared is 9. 5 minus 2 is 3 again, 3 squared is still 9. And 6 minus 3 is once again 3, and 3 squared is 9. This gets us the square root of 27, which is also equal to the square root of 3 times 9. I can pull my 9 out, and that gets me 3 square root 3. The second one, same thing. 7 minus 1 is 8. 8 squared is 64. 6 minus 0 is 6. 6 squared is 36. And 2 minus 4 is negative 2. Negative 2 squared is 4. When I add these up, I get the square root of 104. And this 6. And I can pull my 4 out, so that gets 2 root 26. Part C is a bit different because rather than finding the distance from a point to another point, we're asked to find the distance from a point to the x-axis. So let's actually just go ahead and think about what points on the x-axis look like. Points on the x-axis are always going to take the form x, 0, 0, where this x can be any number. So if I actually just plug this point into my equation, what I get is I would get x minus 1 squared plus 0 minus 3 squared is 9, and 0 minus 4 squared is 16. Well, I want to make this number as small as possible. This part needs to be as small as possible. And the smallest I can get it is 0 because it's squared, so any negative would go to a positive. Well, then the smallest I could get it would be by plugging in x equals to 1, because that is going to make this term equal to 0. So then the distance is the square root of 25, which is just 5. You'll notice that it actually has the exact same x value right there. For part D, we're going to use kind of similar thinking. Points on the xy plane take the form x, y, 0. So again, I can write out a similar square root equation. Here I have x minus 1 squared plus y minus 3 squared plus 0 minus 4 is negative 4 squared is 16. And again, I'm trying, which means each component needs to be as small as possible. This component is going to be smallest when x equals to 1, because that'll make it 0. This component is going to be smallest when y is equal to 3, because that'll make it 0. So then this becomes 0 plus 0 plus 16, which is just 4. And again, if you look closely, you'll notice x equals 1 matches the x component there, y equals 3 matches the y component there. And that's how you find distance. So now let's go ahead and move on to something else. Let's take a look at some vectors. So vectors are pretty important. You'll see them a lot. But first off, what is a vector? A vector has two components: magnitude, in other words, how long it is, and direction, which direction it's pointing in. One thing that they do not have is a starting point. So you'll often see vectors represented as arrows because you can draw the length of an arrow and the direction it's pointing in. For example, I could have a vector like this, and I'm going to call it vector u. So if I have a plane that I'm drawing my vectors on, I can draw vector u right here and there. Now it has a length and it has a direction. Importantly, I can also draw vector u right here because they don't have a starting point. So all that matters is that this vector and this vector are both going in the same direction and they have the same length. So they have the same magnitude and the same direction, so they're the same vector. Let's talk about how we add vectors. Let's say I have a vector u, and it looks like this. And I also have a vector v, and it looks something like this. Well, we like to add vectors using what's called the tip-to-tail method. And all that means is when we want to add two vectors together, we take our first vector, vector u like this, and then we just, wherever vector u ends, that's where we start vector v. Vector starts where we started and ends where we ended. So we can call this new vector, vector u plus v. That's how we add two vectors together. We can also scale vectors. Or in other words, stretch them out or squish them down. So if I have vector u right here, then I can scale it and call this new vector 2u. It's a vector in the same direction as u, but twice as long. So you can think of it as there being one u there and another u there. It's just the vector, but twice as long. I can also take a vector and scale it as it flips the direction around. Also, I can take a vector and multiply it by 0, and that just gets me a point. Now, an important thing to remember is that u plus v is actually the same as v plus u. This is called commutativity. So we can actually see if we take vector v first and then add vector u, is the exact same vector overall. And you might often see this written in like a nice parallelogram, kind of like this. There's vector u as well, there's vector v as well. And you'll notice they just make a parallelogram with our composite vector u plus v as the diagonal. All right, now let's go ahead and do a couple of practice problems before we get into vectors using numbers. And I'll give you about a minute to work through those. All right, let's go over this one. 2v, we just take the vector v, make it twice as long. U plus 2v, we can actually take our original vector u, and we've already found what 2v is, it's that. So then our resulting vector would be this one, and it looks something like that. Of course, all these distances are approximate because I'm not that great of an artist, so there you have it. Finally, we can take our vector u and flip it around. That's the negative u. And same thing with v. And again, we're just using the tip to tail method. That's negative v. And then our composite vector would go something like that from our starting point to our ending point. So the resulting vector would look something like that. Alrighty. So vectors are fine and all, but how do we actually represent vectors vectors using numbers because the arrows really aren't very precise at all. We represent vectors using coordinate pairs. So if I wrote that vector u was 1, 2, what I mean by that is if I plopped it on a coordinate plane, I can plot the pair 1, 2. That would go right here. Then my vector u would go from the origin to point here. And this is vector u. Some of you might have noticed these weird little spiky brackets that I used. Those are often used to denote a vector, although you might also see other things. It's also pretty common to just use parentheses. So you could write it like that as well. By convention, all of our vectors are going to start at the origin. So vector u starts at the origin and goes to the point 1, 2. Again, if we wanted to make a 3D vector, we just have to add another component. So I could do 1, 2, 3, and that's a vector in 3 dimensions. And similarly, it starts at the point at the origin and ends at this point. If we wanted to add two vectors, we just add them by components. So let's say that vector u is x1, y1, z1, and v is x2, y2, z2. Well, then we can just add our two vectors by taking the first component and adding them together. Oh, x1 plus x2, sorry. y1 plus y2, and then z1 plus z2. Similarly, we can scale a vector. So if I have a constant and I multiply it by my vector u, that just gets multiplied into each component. There you have it. Not too difficult. There are a couple of different ways to multiply vectors, although you'll cover that later, so we're not going to touch on it now. It's going to be a bit different than multiplication you've seen previously, though, so don't worry about it too much right now. Just know that it is there. Let's So vectors have magnitude and direction, which means we can almost use them as a way to point from one spot to another. So if I have a point here and a point here, I can find a vector starting at one point and going to the other point. So let's actually just do an example, since I think that's probably the easiest way to figure it out. If I have the point 1, 2, 4, and -1, 3, 7, and I want to find a vector from 1, 2, 4 to -1, 3, 7, I can do that. I just take my second component, the first component of my second vector, subtract the first component of my first vector. In other words, I take this vector and subtract this vector. So I have -1 minus 1, 3 minus 2, 7 minus 4, and the vector that gets me overall is -2, 1, 3. Another way to think about this is the change in x from this point to this point is I decrease y value by 1 and I increase my z value by 3. And that matches exactly what I see in this vector here. All right, let's talk about a really important concept of vectors, and that's their magnitude. The magnitude is also known as the length of a vector. You'll see it often denoted with either absolute value bars like this or double absolute value bars like this. And basically all it is it's the length. So how do we find that length? If you'll remember, a vector starts at the origin and goes to a point. And this point, let's say, is 2, 2, just for examples purposes. This point uniquely defines the vector. So when we have this point, all we need to do to find the length of this line u is we can use the Pythagorean theorem, because we know the vector has to start at the origin. I know the height is 2, I know the width is 2, because that's just the x and the y values, so I can just take them, plug them in. So that's all you do. To find the magnitude of a vector, you just use the Pythagorean theorem. For an example in 3D, let's say we had a vector 1, 2, 4, stealing from the previous example. If we wanted to find the magnitude of it, again, we just use the Pythagorean theorem. That would get us the square root of 21. All right, time for some practice. Let's say we have 3 points. A is 1, 2, 1. 3, negative 1. And C is 4, negative 3, 5. I want to know what's the vector from A to B. You'll often see that written like this. I also want to know what's the vector from A to C. All right, I'll give you guys a few minutes to work through those. All right, let's go over these. First off, a vector from A to B. We can see that to get from 1 to -2, we need a decrease in 3. To get from 2 to 3, we add 1. To get from 1 to -1, we subtract 2. AC, we're going to do the same thing. From 1 to 4 is an increase in 3. From 2 to -3 is a decrease of 5. And from 1 to 5 is an increase of 4. Now for part C, I can actually use my results from part A and B. I take vector AB and add AC. -3 plus 3 gives 0. Let's see, sorry, double checking something. I think I wrote something down wrong on my notes. Right. Okay. So -3 plus 3 is 0. Then 1 minus 5 is -4. -2 plus 4 is 2. Next, I can find vector BC. From -2 to 4 is an increase in 6. From 3 to -3 is a decrease in 6. And from -1 to 5 is an increase in 6. Now, I can go ahead and find out what CB is using the points themselves, or because I've already found vector BC, I know that vector BC goes from B to C, so negative BC would go from C to B, so I can just take negative BC. That would be -6, +6, -6. All right. For part F, first I'm going to need to find out what vector AB plus vector CB is. So I'm going to start by doing that. AB plus CB gives then we have 1 plus 6 is 7, and -2 minus 6 is -8. All right. Now I can plug this into my Pythagorean theorem, and that gives me the square root of 9 squared is 81, plus 7 squared is 49, plus 8 squared is 64. 81 plus 49 is 130, plus 64 is the square root of 194, which could maybe be simplified. 194 is not divisible by 4 though, so I'm just kind of going to ignore it for now. Square root of 194 possibly can be simplified, but that's good of an answer for now. All right, part G. First, we need to find out the magnitude of vector AB plus AC, which we've already found. We can do that using a Pythagorean theorem. The square root of 0 squared plus 4 squared plus 2 squared B minus AC, the magnitude of that. So AB minus AC, we have -3 minus 3 is -6. 1 minus -5 is +6. And -2 minus 4 is -6. All right. And then this vector here, or this calculation, the square root of 4 squared plus 2 squared. 4 squared is 16 plus 2 squared is 20. And here we have the square root of 36 plus 36 plus 36, which is the square root of 20 plus the square root of 108. And again, this probably could be simplified, but I don't particularly care to at this moment, so we're just going to leave it like that. All right, let's go over a few other vector properties. First off, one that's a bit of a review. I mentioned this briefly earlier. Vectors are commutative, which means we can switch around the order that we add them. They are also what's called associative. Oh, I just wrote the same thing there. You want the eraser for that one. And that means we can kind of place our parentheses where we want to when we're adding them. So we can either add B and C together and then add A, or we can add A and B together and then add C. We also have the zero vector. So when we add the zero vector to anything, we just get the same vector we started with. Also, opposite, just negative, whatever vector you started with. So A plus negative A is going to be 0. We can also scale vectors, and they follow the distributive properties. So we can distribute the constant to our vectors. And one important notation difference is for a constant, I don't use the little vector line above them. In your textbook, vectors are usually bolded, but constants are not. So the important thing is they will be bolded. All right. We also have distributivity this way, or we can distribute two constants to a vector rather than a vector, or rather than a constant to two vectors. We also have associativity of multiplication. So we can multiply C and D, our two constants, together, then multiply by A, or we can vector by one of the constants first and then the other. And we also have, whenever we multiply a vector by 1, it just stays the same. So most of these are pretty intuitive. They're just kind of the same properties you've been using your whole life and with the real numbers, but now this time you're just using them for vectors. There are 3 special vectors. And these vectors are known as I, J, and K. And you'll notice I'm actually using a little hat above them, which is what this little pointy symbol is. It's mostly specific to these unit vectors, this hat, but just remember that I hat, J hat, and K hat, as they're called, are the special unit vectors. I hat is a vector 0, J hat is 0, 1, 0, and K hat is 0, 0, 1. And these vectors are really nice because they all have length 1, and you'll notice they all have just 1 in one component and 0s everywhere else. So they're really nice and easy to work with. What this means is we can actually write all the other vectors and K hat. So for an example, let's say we have vector u, and it's 7, 2, and negative 9. Well, I can also write this as 7 times my vector I, plus 2 times my vector j, plus, or I guess minus 9 times my vector k. Really clear, this would be 7 times 1, 0, 0, plus 2 times 0, 1, 0, minus 9 times 0, 0, 1, which is 7, 0, 0, plus 0, 2, 0, minus or plus 0, 0, negative 9, which of course comes out to 7, 2, negative 9. But importantly, you'll notice that my value in my x component there. Similarly, we have the 2 in the y component matching my k vector, and the negative 9 here matching the component there. So that's a really nice thing. We say that these three vectors form a basis for R3, but that's a little more advanced and you probably don't need to know that definition right now. All right, the last thing we're going to talk about is vectors. And a unit vector is any vector with length 1. And we like these vectors because when we have a length of 1, it doesn't really change the length of anything. So these unit vectors are almost like just a direction. The important thing you need to know at this stage is how to find a unit vector given a vector. So if u is a vector, then we can find the unit vector for u that's a vector in the same direction as u but with length 1 by taking the vector u and dividing by its magnitude. So for example, if we have the vector u is equal to 5, 3, square root 2, and we are interested in finding a unit vector, what we can do is first we need to find the magnitude of u. That's going to be the square root of 5 squared is 25, plus root 2 squared is 2. 25 plus 9 is 34, plus 2 is 36, which gives us 6. So then u divided by the magnitude of u would be 1 over 6 times our vector u. And we can go ahead and distribute this 1 over 6 in here, and we get 5 over 6. 3 over 6 simplifies to 1/2, and then we're left with root 2 over 6 as u. So importantly, this vector has length of 1, and we can double check that by going ahead and finding its magnitude. So the magnitude of 5, 6, 1/2, root 2 over 6, we'll go ahead and find. So it'd be the square root of 5 over 6 squared. 5 over 6 squared, 36. 1/2 squared is 1 over 4. And root 2 over 6 squared is 2 over 36. Now we need to combine our fractions. That's the square root of 25 over 36 plus 1/4 is 9 over 36 plus 2 over 36. And this gives us 25 plus 9 is 34 plus 2 is 36. 1, which is just 1. So this vector has a length of 1, so we can say it's a unit vector. Go ahead and find a unit vector in the same direction as v, which is 1, 2, 7. And this one won't come out as nicely as the last one, but good luck. I'll give you a minute or two to work on that. All right, let's go over this problem. First off, we're going to need to find the magnitude of v, which we can do using the Pythagorean theorem again. 1 squared is 1, 2 squared is 4, and 7 squared is 49. So here we're left with 4. And the square root of 54, we can actually simplify down to this being 6 times 9. We can factor out the 9. That becomes 3 root 6. All right, now we simply find our unit vector v divided by the magnitude of v, which is 1 divided by 3 root 6 times 1 to 7. And this comes out as 1 over 3 root 6, 2 over 3 root 6, and 7 over 3 root 6. And this would be our unit vector in the same direction as v. All right, that's all I've got for you today. Thank you everyone who's watching, and good luck in class and have a nice day.